These are the frequently asked questions for Algebra 2 for Section 8.1, Day 2. Starting with number 19, it says fundraising. In a bake sale, you recorded the number of muffins sold and the amount of sales in a table as shown. A says, what is a function that relates the sales and the number of muffins? So what I notice is, as the number of muffins increases, so do the sales, which makes perfect sense. But what that tells us is this is direct variation, which means our model should be y equals kx. And in this case, we're talking about sales, and that's coming from the sale of the muffins. So what I want to do is figure out basically how much each muffin costs. So if I put $12.50 in for sales and 5 in for the number of muffins, that will divide out and give me $2.50 for each muffin. So my formula should really be sales equals $2.50 per muffin. So A says, what's the function? There's the function right there. And then B, how many muffins would you have to sell to make at least $250 in sales? So we're going to put $250 in for S. Sorry, $250. And then, of course, we would divide by 2.5. And that is 100 muffins. Number 20 is talking about doing some painting, and it says the number of buckets of paint needed to paint a fence varies directly, so that's multiplication, with the area, and inversely with the amount of paint in the bucket. And it takes 3 1-gallon buckets, so N is 3 and P is 1, to paint 72 square feet of fencing. So really we have 3 equals 72K, and we would go ahead and divide both sides by 72, and that's going to reduce to 1/24 for K. Now we're going to put that right up here. So N equals 1/24 A over P. Now, what you probably should do when you're writing that is at least put parentheses around that. And this problem really, it didn't ask us to write a model, but we need that model in order to find what we have. So it doesn't matter that I have a fraction within a fraction. If that drives us bonkers, then yes, we could absolutely take care of that really quickly. But you could also just use it as is. And it says how many 1-gallon buckets, so that means the P is going to be a 1. We're looking for N. We have our 1/24, and we need to paint 90 square feet of fence. So really, you just need to figure out 1/24 of 90, and that's 3.75. So this would require 4 buckets because they're 1-gallon buckets for the paint. So use the fact that they are telling you how to set up an equation and then put in what you know and solve for that constant of variation. 21, on Earth with a gravitational acceleration g, the potential energy stored in an object, and we're going to use g as that constant there, varies directly with its mass and its vertical height, h. So on Earth with a gravitational acceleration g, the potential energy stored in an object varies directly with its mass and its vertical height. And that's what we have right there, is a direct variation. In fact, we could describe this as a joint variation. And then it says, what is the equation of potential energy of a 2-kilogram skateboard? Well, that's mass. So what we would do is we would put a 2 in for that. And then just make it look a little nicer by putting the variables behind it. And that's done. They didn't want us to find anything. They just wanted us to put that in. Number 22, think about a plan. The table shows data about how the lifespan of a mammal relates to its heart rate, R. The data could be modeled by an equation of the form RS equals K. So RS will get us our constant of variation. The problem is this is biological, and so the numbers are a little bit off. When you take the mouse and multiply the heart rate times the lifespan, we get 999691200. And when we do the rabbit, we get 996537600. And when we do the lion, 99864, and 4 zeros behind it. So what I chose to do was just to find the average of those. So I added those all up and then I divided by 3. And that is 998289600 for K. So RS equals 998289600. And then it says estimate the lifespan of a cat with a heart rate of 126. So R is going to be 126, and that of course means all we have to do is some division here, but kind of nasty numbers to do that with. So you take the 998289600, you divide it by 126, and we get 7922933 minutes. And you could certainly, figure out, hey, there's 60 minutes in an hour, 24 hours in a day, 365 days in a year, and find out that average lifespan for a cat in years. But they didn't require that. The label in there was in minutes, so you certainly could leave that as it is. Then number 24 says the spreadsheet shows data that could be modeled by an equation PV equals K. Estimate P when V equals 62. So again, our problem is we need to know what K is. So we go ahead and multiply these together, and 140 times 100 is 14,000. Then 147.3 times 95 is 13,993.5. 155.6 times 90, 14,004. 164.7 times 85, 13999.5. 175 times 80, 14,000. Then 186.7 times 75, 14002.5. So this time, as I looked at all of those values, I thought, you know what, I'm just going to use 14,000. If I get the average, it's going to be about that anyway, so I certainly can just get away with using that. So PV equals 14,000, and then it says estimate P when V is 62. So again, we realize we're just going to divide, which makes perfect sense because this is an inverse relationship. As one goes up, the other goes down. And in 24, that comes out to about 226 for the p-value in there. And we can't label it because we don't know what it stood for. They just gave us a spreadsheet there. 26, write the function that models each variation and then find z when x equals 4 and y equals 9. And 26 says z varies directly, so that means you're going to multiply it times x. And then inversely is division. Then they give us the numbers, so it'll be 15 equals k times 6 over 2. Well, that's 15 equals 3k. And we divide through and get a k value of 5. So we substitute that back into the original equation. And then it says figure out what z is. So here's the first part of it. We found a model. If x is 4 and y is 9. So z is going to be 29ths. 2 parts. Write the model, then use it. 29 and 30 tell us that each pair of values is from direct variation. So that's our y equals kx formula, and we're supposed to find the missing value. Well, all I need is one set of x and y in order to figure out what k is. So 5 equals k times 2, 5 halves equals k. So y equals 5 halves x. And now they give me the x value for the second one, so I'm going to put my 4 in for x. So 5 halves times 4, and that will give us 10. Again, there's no label on this one since we don't know what these stood for. Number 30, still using direct variation. We have a 4 and a 6. So 6 equals k times 4. You divide through and do a little reducing. Substitute that in for k. So y equals 3 halves x. And then we notice this time we're getting y. So we have to put the 3 in for the y and solve for x. That means we're going to multiply both sides by the reciprocal, which would be 2/3. And we will get 2 for x because those 3's will cancel out. So with all of these, what's important is when we read through the problem, do we catch on to direct variation or inverse variation? In 35, it says each ordered pair is from inverse variation, and our job is just to figure out what is k. So we need to put the y in the correct spot and the x in the correct spot, and then think about the fact that we're dividing by 3/8. To get rid of dividing by 3/8, you just multiply by 3/8. We don't need anything fancy here. And these will cancel out. The 3's will be gone here, and you can reduce this to 1/4. So that's the k value for number 35. Then for number 36, we have some radicals here to work with. So y is the square root of 18, and x is the square root of 2. So you multiply both sides by the square root of 2, and you get the square root of 36 equals k, which is of course going to give us a k value of 6. So just manipulation here of the formulas. Number 39, each pair of values is from an inverse variation relationship. So I see that I have my x and my y values in that first ordered pair. So I'm going to put that y value of 7 in and the x value of 3, and then multiply both sides and get k. Substitute that back into the original inverse variation, and then use the second point, and in this case my 8 is my x value, to figure out what y is. And there it is. Next set here, we're simplifying these rational expressions. And this is a good reminder that we need to use those absolute value bars sometimes. So in number 55, remember we have a little imaginary 2 out here, and that power, that index that we see there, is actually something we can use for division with variables. So that would give us x to the 5th and y to the 50th. Well, as we look at this problem, we realize originally if people put in negative values for x and y, they were going to come out to be positive anyway. So we need to have absolute value bars around that x to the 5th to ensure that our answer would come out to be positive. Number 57, we're doing 4th root here. So you need to think, okay, what could you raise to the 4th power that's going to get you 64, or maybe we have to break this up. So you start thinking about 2 times 2 times 2, and you get 16. And then maybe you say, okay, well, what about 4? Well, 14 to the 3rd power is 64. So how we would want to break this down would be to say, all right, here's what we really have. 2 to the 4th is 16. And then we'll have a 4th root of 4 left over. The 4th root of m to the 8th is m squared. And then the 4th root of n to the 4th is n. The 4th root of 16 is a 2. The 4th root of 4, we're going to deal with that in just a second. And then m squared, well, whatever I put in there, that's going to come out to be positive. But this n, that's going to need some absolute value bars. Now here's what I want to do. I want to look a little more closely at that 4th root of 4, because that's really the 4th root of 2 squared. And that would really be 2 squared to the 1/4 power. And that's going to give us, by raising a power to a power, 2 to the 1/2. So that's going to become the square root. So this will be 2 square roots of 2, m squared, absolute value of n. And the order is not going to matter here, so we could write 2m squared, absolute value of n, and then put that radical in the back. That's usually the way that we'll work with something like that. Number 58, since the index and the power match, this is just x. But problem, you know, we need to think about what's going to happen depending on whether or not there are positives or negatives put into that function originally. So we need to say to ourselves, okay, what would happen here if we had n as an odd power? Well, if it's odd, then your answer is just x. So for an odd n value, everything's good to go. However, we know that if that n is even, then we have to make sure that it comes out positive, and that's those absolute value bars. So that would be for an even n value. So really thinking about domain in that one as far as getting everything exactly where we need to go.